So far we have seen that given the point correspondences between two views, how we can recover the fundamental matrix F in an uncalibrated setting. And we have seen that by recovering F, which is the fundamental matrix, we can decompose it into a pair of camera projection matrices denoted by P and P prime respectively. Although we also seen that the decomposition is not unique. This means that there's a whole set of solutions of the camera projection matrices that can satisfy the decomposition of the fundamental matrix given by P multiplied by a 4 by 4 non-invertible H matrix, which is a projective transformation, and P prime multiplied by H over here. And in the calibrated setting, we saw how to get the essential matrix. This is the calibrated setting using the image correspondences as well as the known camera intrinsics value denoted by K and K prime. And we saw how this can be decomposed into the rotation matrix and the translation vector that relates the two views. And together with the camera intrinsics value, we can recover P and P prime, which is the camera projection matrices of the two view uniquely. So now, suppose that we are already given P and P prime, or we can compute P and P prime from the fundamental matrix or the essential matrix respectively, together with the point correspondences. Can we recover the 3D point that gives rise to the point correspondences X and X prime? The answer is yes, we'll make use of what we call the linear triangulation algorithm to achieve the reconstruction. And we have looked at in the past lecture that in each image for a given 3D point, we would have the projection of these 3D points onto the 2D image given by small x equals to P multiplied by X in the first camera view, and X prime equals to P prime multiplied by X, which is the same 3D points in the second view over here. And we can see that this equation here is actually defined up to a certain scale. So X equals to P multiplied by X. It can be scaled using a scalar value lambda, and this is valid over all values of lambda. So we can actually take the cross product on both sides by doing this, such that it will equate this particular equation in a constraint over here, and the scale can be removed over here, which is equivalent to X cross with P and big X over here equals to 0. Similarly, we can do the same thing for the second view, which gives rise to this equation here, X prime cross product with P prime of X equals to 0 over here. And what we can see here is that each one of these equations in the respective view will give rise to 3 equations over here. That means that there are altogether 3 constraints over here, but only 2 of them are linearly independent. So that means that we will only have a remaining of 2 constraints per view on each particular point correspondence. And what we can do here is that we can stack these 2 equations from each view together. So the first 2 equation is from the X, and then the second equation is from X prime. So X as well as P, and X prime as well as P prime. So we can stack them together to form a 4 by 4 matrix A over here, which we multiply by the 3D point, because we can linearize this by factorizing out the common 3D point over here into this homogeneous linear equation over here, where X is the unknown 3D point given by X, Y, Z, and 1 over here. And we can solve this equation over here. For every point correspondence, we will get one of this equation, which is an overdeterminate equation, since there's only 3 unknowns inside this particular 3D point over here, and we have 4 equations. So this is sufficient for us to solve for the 3D points uniquely. We'll simply follow the same step of taking the SVD of A. So the SVD of A will give us U sigma V transpose. And the solution of X will lie in the least singular vector inside V, which we denote as V4. And furthermore, since we know that the last element of X is going to be always equals to 1 over here, so what we can do here is that we can simply divide v4, the vector v4, by the last element. So v4 here is going to be equals to v4x, v4y, v4z, as well as v4w. So we can divide the first three by v4w to make the last element of x over here to be equals to 1. So now let's look at the reconstructed point with known camera calibration, which means that we start the reconstruction from the camera projection matrices that is recovered from E and the known camera intrinsics K and K prime. So E here, as a reminder, we will be able to recover R and T, and together with K and K prime, we'll be able to recover P and P prime uniquely. So we'll see that by making use of P and P prime in the linear triangulation algorithm that we have seen earlier on, the 3D structures that we recover from the linear triangulation algorithm is subjected to a similarity ambiguity. We'll see why is this so. So let's denote HS as any similarity transformation. This is a 4x4 matrix where the first 3x3 is a rotation matrix and the last 3x1 over here is a translation vector, and there's a scale factor which we denote as lambda in the last element over here. So we can see that according to the camera projection equation, let's denote this particular point as xi over here. It projects onto the image here as a small xi, and this is equivalent to p multiplied by xi over here. And what's interesting here is that the same point on the image can be also obtained from another projection, which is given by p of hs inverse multiplied by hs multiplied by xi over here. What this means is that we can distort this particular 3D point using a similarity transformation here, and as well as the camera projection using the similarity transformation, and we can see that this will still fulfill the projection function over here, where the distorted 3D point will still project back to the same image coordinate over here. We know that the 3D structure is going to be scaled up or scaled down according to the similarity transformation. And what's interesting here is that we can see that the resulting camera projection matrix is still a valid camera projection matrix. So starting from the original camera projection matrix, say it's denoted by K, RP, and T over here. If we multiply by this by a transformation of HS, we can see that the end result here is still a valid camera matrix, where K here is still the intrinsics, whereas the rotation and translation would be deformed by the similarity transformation here. And in the case of a uncalibrated camera, which we have seen earlier on, that we can make use of a fundamental matrix computed from the 8-point algorithm to decompose this into two camera matrices, P and P prime. And we saw that this is not unique. In fact, there is a whole family of solutions that fulfills this decomposition, which is under a 4x4 non-singular projection matrix given by this particular relation over here. And we can rewrite this into inverse of this. Since this H over here is a linear mapping which is invertible, so let's denote this in order for us to prove this relation as in H inverse over here. So now we can see that the point, the 3D point, is reconstructed as X over here from the linear triangulation algorithm using P and P prime. It is still a valid reconstruction. What this means is that if we take the projection of X that is reconstructed earlier on using the camera projection matrix onto the image X over small x over here, this would be equals to P multiplied by capital X. And if we were to take this and the 3D structure that is recovered earlier on and distort it under a projective transformation denoted by H over here, we can see that if we apply the same projective transformation onto the camera projection matrix P, where PH inverse and P prime H inverse will give rise to the same fundamental matrix as P and P prime over here. So this means that this pair over here, they are also a valid decomposition of the fundamental matrix. And we can see that under this particular decomposition, and as well as the distortion of the 3D reconstructed point by the projection matrix H over here, it will still be projected onto the same image point X over here, simply because we have PH inverse multiplied by HX over here is equals to P of X, which is equivalent to the original projection under the original setting. But in this case, we'll see that the reconstructed 3D structure is actually subjected to a projective ambiguity. And here is an example of the reconstruction under projective ambiguity. Given original image pair over here, we can take some point correspondences, at least 8 point correspondences, and compute the fundamental matrix. So in this case, it's an uncalibrated case, and we know that we can decompose this into P and P prime that is subjected to a projective ambiguity that we have mentioned many times. And by making use of these decomposed camera matrices, we can reconstruct the 3D structure, and we can see that this 3D structure is subjected to a projective ambiguity as what we have seen earlier on, where in this case, parallel lines are no longer parallel and points at infinity where parallel lines should meet. So these two lines are actually parallel lines. So we can see that these two lines actually meet at a certain finite coordinate and is no longer at an infinite point. Now, we'll introduce the stratified reconstruction to remove the projective ambiguity in the reconstruction from the camera matrices that is obtained from the fundamental matrix. And as we have mentioned earlier on, or as we have seen earlier on in the first few lectures, that the stratified reconstruction or the stratified approach simply means that we're going to remove the projective ambiguity in a two-step approach. We'll first remove the projective ambiguity and transform it into a reconstruction with an affine ambiguity. Then finally, in the second step, we are going to remove the affine ambiguity to recover the metric reconstruction. We will see that these two steps has to be done with some information from the scene. The first step to stratified reconstruction is to do affine reconstruction. In this particular step, we'll remove the projective ambiguity. So the essence of the affine reconstruction is to first locate the plane at infinity. And the idea here is very simple, because under projective transformation, it is possible to map the plane at infinity under a projective transformation. We know that a plane at infinity can get mapped onto a plane at a finite coordinate. And so now the first step of the affine reconstruction, because under affine ambiguity, a plane at infinity is still going to be mapped to a plane at infinity. So the first step in affine reconstruction is to identify the plane at infinity and find a homography that projects the plane at infinity, which is now at a finite location. We are going to find the homography that maps the plane at infinity, which is now at a finite location, back into the plane at infinity, which is given by the coordinate of 0, 0, 0, 1 over here. And we can see easily that this particular homography, which is H over here, to map the plane at infinity, which is now at a finite location, back into an infinite location. That is, this homography is actually given by this equation over here, where pi over here is a 4 vector that represents the plane at infinity under projective distortion. So if we can identify this particular plane over here, we can simply compute the homography over here. And by making use of this homography, so we can map this particular plane back into the plane at infinity. I'll leave it to you to verify this. You can easily substitute pi over here, multiply by pi over here, and this is going to give you 0, 0, 0, 1, which is the plane at infinity. Once we have obtained the plane pi and the homography h over here, the next step is simply to map all the reconstructed points, which is denoted by x over here, into x prime to remove the projective ambiguity. And hence, we are able to get a affine reconstruction from here. The plane at infinity, which is under projective distortion, can be identified if we know that in the scene which set of lines corresponds to parallel lines. So we will just simply need to know at least 3 sets of parallel lines in 3 different directions in order to find the plane of at infinity. For example, this is the reconstructed 3D structure with projective ambiguity. So if we know that these 2 lines corresponds to the roof, they are supposed to be parallel line. We can simply take the intersection of these 2 lines to find the vanishing point, which we denote as V1 over here. This V1 is simply equals the cross product of these 2 lines. Let's say these 2 lines is represented by L1 and L2 here. It simply equals to the cross product of L1 and L2. And similarly, we can identify another 2 sets of parallel line to give us V2 and V3. So pi here, the plane at infinity is supposed to contain, so this particular plane at infinity is supposed to contain V1, V2, and V3, because these are ideal points, vanishing points that are supposed to lie on the plane at infinity. But in the case of under projective ambiguity, or projective distortion, we can see that all these 3 points now are in a finite location, as well as the uh, plane at infinity is also at a finite location. So, but we can simply define this plane, which is now at a finite location, which we denote as pi, as the cross product. So we can take these 2 points and take the cross product, which is going to give us this line over here, as well as V2 and V3. We take the cross product. So this is V1 cross with V2, V2 cross with V3 to give us these 2 lines over here. And the cross product of these 2 lines is going to give us the normal vector that represents this particular plane over here. So once we identify the 3 vanishing points, we would have already identified the plane at infinity. And once we get this, the plane at infinity, we can easily compute the homography to remove the projective distortion. So this is how it looks like after the removal of the projective distortion by applying the projective transformation that we have seen earlier on, which is H that is given here. And this is how it will look like after the removal of the projective distortion. And what we will see is that now parallel lines becomes parallel, and the plane at infinity, or the parallel line, will intersect at the plane of infinity, which is located at an infinite location. But what remains would be a affine distortion, where the angles between lines are not recovered and they still remain distorted. So after we have removed the projective distortion to recover an affine reconstruction, the last step of the stratified reconstruction is to remove the affine distortion to recover the metric reconstruction. And the key to achieve this is to identify the image of absolute conics omega. We'll see that we'll make use of this image of the absolute conics omega to define or to retrieve a 4x4 matrix H, projective transformation matrix H over here, such that we can apply this particular transformation or all the reconstructed 3D points under affine distortion to recover all the 3D structures in the metric reconstruction over here. And this particular matrix H over here, the first 3x3 entries is given by A matrix inverse, and the last element is 1 over here, where A is simply recovered from the Kolosky decomposition of this matrix over here, where M here is the first 3x3 entries of the camera projection matrix in the second view, and omega here is the image of the absolute conics that we have identified earlier on. So now let's proceed to prove that this relation over here is true. And we have seen earlier on that under known camera calibration, VK prime over here, of the second view, the camera projection matrix in the second view, PM prime over here is simply equals to the camera intrinsics K prime multiplied by the extrinsics represented by a rotation and a translation. And this is subjected to similarity distortion, which we have seen earlier on. We also define in this particular case that a finely distorted camera matrix is given by P prime M, where the capital M is a 3 by 3, and the last column here is represented by small m over here, which is the case that we have seen earlier on here, that is used to define the 3 by 3 matrix of A. And now we can see that this particular matrix over here, P prime, it can be projected under the 4 by 4 transformation of H into PM prime from this relation over here, where H inverse A equals to this guy over here, which is simply the inversion of this matrix that we have defined earlier on. And what this means is that if we apply this H inverse here back into this equation and substituting all the expressions here and here into this equation over here, we'll get this particular relation where we can see that K prime R is equals to M multiplied by A in the first 3 by 3 entries over here. So from the previous slide, we saw the relation of MA equals to K prime multiplied by R, and this can be rewritten into MA multiplied by the transpose of itself, and that would be equals to K prime multiplied by R multiplied by K prime R transpose, where we can rewrite MA transpose to be equals to A transpose multiplied by M transpose, and similarly we can rewrite K prime R transpose here to be equals to R transpose K prime transpose here. And since R here is an octagonal matrix, this means that R here multiplied by the transpose of itself would gives us identity, which means that R here can be cancelled out. And this gives us the relation that we see over here, M multiplied by A transpose multiplied by M transpose equals to K prime transpose here, where we can simply move M to the right side of the equation to give us this relation over here. Here we notice that K prime transpose here is what we have defined to be the inverse of the image of absolute conics in the previous lecture, which we can denote this as omega star, or simply equals to the inverse of omega. And here this relation here would give us A multiplied by A transpose equals to M transpose omega M inverse, which is the equation that we have seen earlier on here in the previous two slides. And once we get this relation over here, we can apply the Cholesky factorization on A transpose, or simply on this guy over here that we have computed to recover A, which we can plug into this equation over here to obtain the 3D transformation for metric reconstruction. Here we know that M here is from the camera projection matrix, and omega here, which is the image of the absolute conic, can be obtained from the various methods which I have mentioned in lecture 6. So finally, after we have recovered the H matrix or the A matrix over here from the image of absolute conics, we can simply apply this H matrix onto the affine reconstruction to recover the metric reconstruction, where we are still subjected to only a similarity transformation, but we can now see that the angle are now recovered, as well as parallel lines, they become parallel. So in summary, we have looked at the various definitions of the terminologies used in epipolar geometry that can be used to describe the two-view relations. And we have looked at how to compute the epipolar line from the fundamental matrix. So this is essentially L prime equals to F multiplied by X, that we saw that the point gets transferred to a line from the first view to the second view. Then we have looked at how to compute the fundamental and essential matrices under uncalibrated and calibrated settings with 8-point correspondences. Then we look at given a fundamental matrix that we compute from the 8-point correspondences, how to decompose this into P and P prime respectively. And we also look at how to decompose an essential matrix, which is under a calibrated setting, into the rotation and translation between two views. And finally, we look at, after we recover either the fundamental matrix or the essential matrix, how to recover the 3D structures from the point correspondences using the linear triangulation algorithm. And under the uncalibrated setting, we look at how to do stratified reconstruction to remove the affine as well as the projective ambiguity. Thank you.